So I want to write these equations in time domain as like we know s plus a divided by s plus a whole square plus b square is e power minus at cos bt. Similarly, whenever you have b by s plus a whole square plus b square, then e power minus at sin bt. So these two formulas I want to use in this particular equation. Therefore, we already got that standard form. What is that? C of s is 1 by s minus we have s plus zeta omega n divided by s plus zeta omega n whole square plus omega d square, plus we have zeta omega n by omega d into omega d divided by s plus zeta omega n whole square plus omega d square. So in this case now everything is in a standard. Therefore directly I can apply inverse Laplace transform. Then that will be, when you apply inverse Laplace transform, your C of t expression is going to be C of t is equal to 1 by s becomes 1 minus e power minus zeta omega t cos omega dt plus e power minus zeta omega t sin omega dt. So here I have e power minus zeta omega n t, here I have e power minus zeta omega n t. So I can take common. So when you take common, it becomes 1 minus e power minus zeta omega n t. Then you can open the bracket, then you can write it as cos omega dt plus, and already we have zeta omega n by omega d sin omega dt. So in the next step, already we have taken e power zeta omega n t common. Now in the second, in the sine term, there is zeta omega n by omega d. We know omega d is omega n into 1 minus zeta square under root. So when you replace that alone, then we can cancel omega n, then the remaining is zeta by square root of 1 minus zeta square. So if you do that, the other terms are same, then it results like this. Your C of t is equal to 1 minus e power zeta omega n, then zeta omega n t, then we have cos omega dt plus zeta by square root of 1 minus zeta square sin omega dt. Now I want to take the denominator of the sine term, that is zeta 1 under root 1 minus zeta square common. So now C of t is equal to 1 minus e power minus zeta omega n t divided by under root 1 minus zeta square. Now, so inside we have under root 1 minus zeta square cos omega dt plus zeta sin omega dt. So if you look at the damping ratio triangle, we know that the sin phi is under root of 1 minus zeta square, cos phi is zeta. Now I want to replace here in this equation. What will be the result? The result is your C of t is 1 minus, the common terms are already there, e power minus zeta omega n t divided by under root 1 minus zeta square, and inside in place of under root 1 minus zeta square I can write it as sin phi into cos omega t plus cos phi to sin omega t. So this is like sin a plus b, where a is omega dt and b is phi. Hence we can write C of t as 1 minus e power minus zeta omega n t divided by 1 minus zeta square under root into sin omega t plus phi, where phi is a cos inverse zeta or tan inverse under root 1 minus zeta square by zeta. So this is the complete expression of step response of underdamped system. Now I can use this expression to draw or to plot what will be my underdamped response for a unit step input. Before that, what are the terms that are available in this C of t expression? Now as you know, any time response has both the transient as well as the steady state. So what is the transient term here? The transient term is wherever you have e power term, that is a transient term, and constant is 1. Therefore 1 is the steady state and the other things are transient. Still in the transient, I have two important parameters. One is the e power term, in that I have zeta omega n, and also in sine term I have omega d. Therefore, if you look at two differently, your e power minus zeta omega n t term will have exponentially decaying response. Then what about sine omega dt? Sine omega dt will give a continuous oscillations with a frequency of omega d. So whenever combine these two, then the resultant response will have continuous oscillations, but those oscillations are dying out. So those oscillations will die out because of your e power zeta omega n term. So you can look at here how the response is. This is your time and this is your steady state value. So it rises and it falls back and rises, and some oscillation it's going, and after some time, and those oscillations are dying out, and it will have a steady state response. So the C of t expression, you can easily predict what kind of response you are going to get. So that will, steady state is 1 I said, and we have oscillations, and those oscillations are dying out. So zeta omega n t is a term which is responsible for your exponential decay to die out the oscillations, and omega d is responsible for oscillations. Now, so under steady state value, under steady state condition, your C of infinity is, so from the response directly you can say your steady state term is 1, and even if you apply final value theorem, then you can say what will be the steady state value. The steady state value C of infinity is going to be 1. Then to find the steady state error, the steady state error is E of infinity is R of infinity minus C of infinity. We know that for step input, unit step input, your R of infinity is going to be 1, and just now we have seen your C of infinity is also 1. 1 minus 1 is 0. Therefore, the steady state error is going to be 0, which means, so the system, any standard second order system, when you apply step input, not only the unit step input, when you apply step input, the steady state error is going to be 0. Now, if you apply the same step input for different values of zetas, now when zeta is 0, we know it is called underdamped system. For underdamped system, what will be the step response? So we can directly write here, there is a derivation, but I want to see only the output equations. Your C of t is 1 minus cos omega n t. So we have cos omega n t 1 minus, therefore we have continuous oscillations. Similarly, when zeta is 1, it is called critically damped. Your C of t expression is going to be 1 minus e power omega t into 1 plus omega n t. So when zeta is 1, we say we don't have any oscillations because there is no sine term at all, but your response will rise like this fastly, and it try to reach us to the steady state value as fast as possible. Now the last case, when zeta is greater than overdamped system, and for this we will have the step response C of t is equal to 1 minus e power minus zeta minus underscore zeta square minus 1 omega n t divided by, then I will have 2 into square root of zeta square minus 1 into zeta minus under root zeta square minus 1. So this response will give us a slowly increasing response, and it is going to the steady state value, which is a sluggish nature of the system. Now for these zetas, and if I give the input, then all 4 responses, how they look at. Now look at this image, this graph. It's a beautiful graphical representation of variation of your C of t for a step input when zeta is varying from 0 to 1 or 0 to infinity. Means I am taking only 4 distinct values, not in between values. That is, zeta is 0 and zeta is in between 0 and 1 particular value, and zeta is 1 and zeta is greater than 1 particular value, and all 4 responses will vary like this. Then you can look at, so you have very fast response increasing and oscillating for undamped, and your underdamped also fast but slower than your undamped, but we have it is going, it's have its own oscillations and it's dying out. So your critical damp will rise like this, and it is going to steady state value like your first order, and of course the last one is very sluggish, slowly it is increasing. So this way we can look at different kinds of responses for the step input of second order system.